All right. Hello, everyone. Welcome to Housing 2.0. This is our fourth virtual seminar that examines how to consistently optimize 5 key housing user experiences. Now, today's seminar is going to focus on getting to zero for lower cost. We're going to share some tips and some tricks with you to help you build net zero homes and communities for a higher profit. I just hope that you'll remember what we say, seeing as how this is Memory Day and all. Now, my name is Mike Collignan, and I'm the Housing 2.0 Program Manager. And if at any point you have questions, please don't hesitate to reach out to me via the chat box, or you can also reach out to me by email. I'm going to put that email address into the chat box in just a little while. You know who's forgotten more about housing than I know? Sam Rashkin. He's formerly the Chief Architect at DOE's Building Technologies Office, but now is focused on creating and teaching the content for the Housing 2.0 program. That content is based largely on Sam's latest book, Housing 2.0, Disruption Survival Guide. The full program was established to help empower you, our building professionals, to design and construct higher performance, healthier, and more sustainable homes at a fraction of the cost. Sam's going to lead us through today's seminar and also address your questions at the end. Now, before we get started, I want to tell you about our memorable sponsors. The first is Schneider Electric, who is driving the digital transformation of modern homes with smart and sustainable energy solutions for ultimate comfort and energy efficiency. Their connected home ecosystem of smart energy management solutions provides digital control of energy use throughout a home, from the grid via their smart electrical panel to their connected wiring devices. Next, we have Jinko Solar. They are a leading PV module manufacturer and energy storage system integrator. The company has deployed approximately 110 gigawatts of their Eagle modules in 160 countries globally, including more than 17 gigawatts right here in the United States. Eagle Storage brings together the best energy storage technology for turnkey hardware and energy storage services. And finally, we have Panasonic Healthy Indoor Living Solutions. They're helping builders across the country differentiate themselves with powerful, code-compliant, and cost-effective indoor air quality solutions that provide a safer environment for home buyers. Now, during the course of today's presentation, you can submit questions for Sam. Simply use that questions box inside the GoToWebinar panel. I'm going to review those questions and pose them to Sam after his presentation. All right, time to hand it over to a guy whose name is, that's right, I remember you. Sam Rashkin.
Hey, thank you, Mike, and welcome everyone. Like Mike, I'm incredibly grateful for our sponsors. They are carefully curated to align with our interest to help housing professionals bring the best homes to American home buyers. So today's topic is really important to us, zero for lower cost. We're dedicated to zero and high performance builders being industry leaders, and a absolute requirement is that there are homes that people can afford. So today's webinar is really important, and it's going to pull from a lot of other webinars we've done to try and create a whole framework for how we can do this. So let's start right in with the outline. First, we'll review the context, why, what, and how drive Housing 2.0. Then we'll go into why there is a lower cost imperative for zero and actually all homes. Then zero building blocks that we need to address to be successful getting to zero. And then the strategies for how we get zero to lower cost. And like all our webinars, we reserve time at the end for all questions that you have. So let's jump right in and talk about the context, why, what, and how. So it all starts with the basic data of extensive research where people spend their time. And what we find, we look at all the places we go to every day, where we live every day. Home, our residence, is where life happens. We're there 70% of our lives. And if I take a guess where we're at post-COVID, since these were done way before COVID, probably the numbers are getting closer to 75% of our time every day is in our home. And so what Housing 2.0 is about is homes where life happens better. How do we look at holistically? Housing is a system. Much the way the high performance building science industry will look at the house as a system, we look at housing as a system. It's the ultimate consumer product. And how do we make sure the high performance zero energy homes are industry leaders when it comes to user experience? So what we do is recognize a framework for how we can do this. There are 5 user experiences, 5 strategies, and 160 best practices that we can deploy to consistently deliver a better user experience. Now, if all we do is focus on one of those strategies, high performance or zero energy, it's not likely this tool is going to stand up. So that's why for us, it's critical that this framework addresses the comprehensive set of experiences every home buyer expects: community, design, performance, quality, and sales. They may not verbalize it this way, but this is what expectations are. So how do we get there is the essence of this program. There's a first cost business model, and then there's a housing 2.0 business model. In the first cost traditional business model, US optimization is done by minimizing investments in experts and special features. In housing 2.0, what we do is we go do extensive kind of evaluation of the user experience, and where we can identify really transformative user experiences, we make the investments in experts and special features that can deliver them on budget. And the secret sauce to the whole framework and process is what we do after that, where you have costs for material, labor, and marketing with a traditional first cost business model. In Housing 2.0, we apply this incredible lens for optimization to get substantial savings from simple, lean, quality, integrated systems, and mass customization. The result is that you wind up with these cost savings on net because the savings exceed the extra investment in optimization, and you wind up with this added value, better user experiences, and substantial owner cost savings. So the final step is to translate all this value during the sales process to sell, service better homes for lower cost. We find when we do all the tabulations that the combination of the added value and cost savings can be 30 to 70% of the cost that we build today. So these are huge opportunities, and the key resource for you is a book, Housing 2.0 Disruption Survival Guide. You can just take a screenshot of the code on the right to get right to where you can order the book at the Green Builder Media website. But this is the resource. It has over 400 pages. It has over 360 citations. It has 8 guest expert essays. It's got hundreds and hundreds of graphs and charts and illustrations. It is the unique singular reference on how to optimize user experience in high performance homes. So I hope you do take advantage of this. So let's jump in and look at the zero for lower cost imperative. And it all starts with this chart. This is everything you need to know about why housing has an affordability crisis and why it's not sustainable. When you look at the median home price in blue and the median household income in the black curve, you cannot have this kind of widening gap between price and income. At some point, the buyer has to be able to afford the house. And today, over 2 times the median income is needed to afford a home, or in 2021, it's even worse today. So it's $144,000 is required to buy a home when the median income is less than $70,000 nationally in the country. And when you look at basically the curve itself, you should also be concerned. Every time you have a rising peak like this in housing prices in the past half century, it's been followed by a very difficult recession. And here we have a historic peak, probably greater than any other preceding it. And that's why many, like experts, including myself, forecast that there has to be some correction in the industry. We don't know how much and how deep it will be, but again, this is not sustainable. And also of concern is that 2023 was the least affordable year for housing on record. And look at some of the numbers from 2022. This was a Harvard University Joint Center for Housing Study kind of set of results. Price to income ratio we just talked about in the 100 largest markets is now greater than 5.0. 3.0 is kind of considered the upper threshold of affordability. Now in 2000, only 5 markets were greater than 5.0. As recently as 2019, it was 15 markets. And in 2022, 48, half of the 100 largest markets, the price to income ratio is greater than 5.0. And we had all-time high price to income ratios in nearly 80% of the 100 largest markets, 78 in 2022. And so compare that to 2000, when 2/3 of the 100 largest markets, that ratio was below 3.0. It was in the affordability range. And so, you can see I highlighted at 5.6 is the median home sales price and median household income ratio in 2022 compared to 4.1 in 2019. And when you're greater than 5.1, you're considered severely unaffordable. Again, that threshold of 3. So we're in uncharted territory. Something's got to bust. We can't keep going up higher. And so we see it kind of in some of the market indications. Renters just don't see any path for so many of them to how they'll ever get to home ownership. 60% worry they'll never be able to own a home when over 80% want to own one. And you don't need even to look at the direct housing statistics, just look at the financial well-being statistics for American households. 40% can't pay an unexpected $400 expense. Nearly 2/3 are living paycheck to paycheck. Over 60% are worried about how they're going to pay for housing next year. And there are a whole host of related indicators that are really scary that have to do with delinquency and car loan payments, rising foreclosures. Americans are house poor. The price structure is not working. So this all informs how we look at zero energy, and it starts with first, let's look at what are the building blocks to get to zero. And so I'm going to start first with the first thing we know we have to do is optimize energy efficiency. And National Renewable Energy Laboratory has a tool called BOPT for helping analyze a lot of optimization factors you see on the right for how you can get to least cost. And you start with point 1, which is the reference case. Often it's the local code in your state or jurisdiction. And when you see this bar chart, the red is your utility bills and the blue is the incremental mortgage for going above the reference case. So in point 1, obviously it's all the utility bills that are the energy related costs. And what we do in optimization is keep trying to make investments in energy efficiency measures that wind up reducing the energy costs greater than the incremental mortgage. So the costs go down because when you get to point 2, you have the minimum annual energy costs on the path to zero net energy. You see the increase in the incremental mortgage to pay for those energy measures, but because utility bills go down much greater than an increase, your net energy related costs are lower. And this point is considered the minimum most cost effective point. But we can still make further investments in efficiency and still be below point 1, which is the baseline reference case. And so when we do that, the next point is point 3. That's the takeoff point where the next incremental investment in energy efficiency is actually costing more than an investment in solar. So point 3 is just that takeoff where now you would consider solar, again, based on these optimization factors that the software considers. And then point 4 would be how you can get to net zero energy, where you have we have no energy bills, but your mortgage keeps going up because of the extra cost of solar. So you're producing as much energy with solar as a house consumes on an annual basis, but now your point may be higher. Your energy related costs may be higher than the point 1, the reference case. And what happens over time is that solar costs keep coming down. So you could be at point 1 or actually below point 1 with your net energy costs. And this is what we strive for. And the key thing I make about this analysis that I always am frustrated that it's missing is there's so many other optimization factors that really drive the true cost. Cycle time, cost of quality with different choices that are made, risk, rework, embodied carbon, non-energy benefits, health, comfort, resilience. There's so many factors. It's a much more complicated decision, but hopefully this concept helps you understand what we're doing to try to get on the path to net zero, starting with energy efficiency and optimizing. The next thing we have to do is manage risks, because what happens when we go from a low performance to a zero energy enclosure, we go from less insulation to more insulation, and we go from less air tightness to more air tightness. So the thermal and airflow through a low performance, non-zero energy home is very substantial, and it's reduced tremendously when we do the zero energy solutions. What winds up happening as a byproduct is we create colder surfaces on the cold side of the assembly inside the outboard layer. So it's drywall in hot climates, and it's the outboard sheathing in cold climates where the cold side will be. And that all this whole dynamic creates much greater risk. First, moisture, we have more wetting potential with the colder surface and less drying potential with less heat flow moving through to dry any wetness that might occur, condensation, or particularly through bulk moisture issues. So we have to really manage bulk moisture almost at a militant kind of level. The next thing to manage risk is we have to recognize we have ultra low load homes. So comfort completely changes and is more risky. Historically, we've not been very diligent about our thermal distribution system for heating and cooling systems. And now that we create even dramatically lower airflow, will we have good mixing and comfort throughout the home when historically we don't address really good duct delivery systems? The other two have to do with moisture comfort. Shorter cycles in the summer, because the sensible loads are so small, will mean we get less accidental dehumidification from the air conditioning system. So will we have enough latent load management, keep humidity under control? And similarly, on the front and back ends of the seasons, they shrink because, again, the sensible loads are so much lower in ultra low load homes. So we have no air conditioning for an extended time, maybe into May or June, and it shuts off earlier at the end of summer. So what happens in those swing seasons to manage the latent loads that are still there? So comfort is a bigger risk in zero energy homes. And lastly, since they're so much more airtight, we have less dilution of contaminants, so managing contaminants in homes is a bigger risk. So it's not that this is bad, it just means this is what we do when we build zero. We have to manage these risks. And lastly, we have to recognize zero energy homes are really configured to stand the test of time, to meet expectations for where we have to be in the future. But there are all these hard trends that are acting on housing that have to also be integrated beyond being efficient. There are incredible increase in frequency, magnitude of disaster occurrences, so we have to recognize we have more disaster risk. Water shortages are profoundly increasing across so much of the country, west of the Mississippi. And all this transition to all electric that's left the station. What are we doing to make sure our homes can adapt to the all electric future that's just almost locked in for the near term? So these all have to be managed. So this understanding helps configure the key building blocks for how we get to zero energy. One, recognize that zero energy homes are compelling because they live better. And what we do is first optimize efficiency. We optimize enclosure. We optimize equipment. We optimize components. It's very basic and it's order of importance. Enclosure first, equipment, components. Then we manage risks. Moisture, comfort, indoor air quality, ones we just spoke to. Third, we then also want to make sure we're future ready. We have homes that are worthy and should last hundreds of years if they're prepared for the future. So we make them disaster ready. We make them water efficient in locations that have risk of droughts and low water supply. And we make them electric ready, knowing that's where the industry is going. And finally, we just recognize that we have to get on the path to zero with one of any number of solutions. We get to zero with on-site solar. We can use microgrids, utility solar, carbon offsets. We have lots of options for how we offset any residual energy consumption after we do all this good work on the front end. These are the building blocks for getting to zero. So zero lower cost strategies. What do we, how do we do this at lower costs? We have this affordability imperative, and we know what we have to do to get to zero. And I'm going to suggest there are 5 key strategies. And if there's a key message here, it's that so much of the focus in the industry is primarily on the energy side of the equation, and that won't get the job done. You need to optimize design. We need to optimize mass customization. We need to optimize then the enclosure and HVAC, which are traditional focal points for getting to zero. And fifth, we need to optimize productivity. We can't keep building the same way we're building and expect to get to the cost savings and cost points we need for housing affordability. So we can't just do the enclosure and HVAC and ignore those. Now, health will never go away as a critical need for zero energy homes, but it's not, it's just not a strategy for lower costs. It's something you have to do. So I leave it off the list just to kind of mix any people who might be jumping and objecting, where's health? It's just a must-have. But to get to lower costs, the strategies that get you there are this: design, mass customization, really optimizing the enclosure, optimizing the HVAC, and really figuring out more productive ways that we can build. And so this is much more all-encompassing. It's looking at housing as a system, not just the house as a system like we normally do with building science. So let's start with design first. And one of the strategies those that attend our design workshops know I'm a big advocate for is natural comfort. And the big reason, it's free. It costs no more to exploit the free resources of the sun and the wind for natural heating, natural cooling, natural fresh air, and natural lighting. And the objection always we hear to this is, well, I'm getting my lots from the developer or subdivider of the property, and I'm stuck. And my answer to you is you're not stuck. Probability is that 25% of your lots will have a south real elevation, 25% of your lots will have something approximating a south front elevation. So you should have designs ready to go, or strategies for design ready to go to exploit natural comfort for 50% of your lots that either face front or backyards to the south. That's just what we should do. And the key is solar orientation. And it's because that is an absolute must-have to optimize access to this solar resources of the sunlight, and also to optimize control of that sunlight. So it's not detrimental in the summer, and it's helpful in the winter, and optimize daylight throughout the year. On east-west orientations, you have minimum access to that solar resource and minimum control. It's so low in the sky. And north orientations are only diffuse light, so there's no solar resource to leverage. So the key point about this orientation also is that once you do it, and this is a very great concept layout that shows how you can get 100% solar in a subdivision, you get automatically 25% free heating and cooling. And if you're a utility provider, it should be worth a lot to you, because maybe you need 1/4 of the capacity at the power transformer station because of the lower demand for peak cooling. So that's your start. But then you have this whole suite of tools, solar shading, thermal mass, prevailing breeze orientation, window placement with wing walls or casement window direction that they open, and cool roofs to then leverage all the full suite of natural comfort: natural heating, natural cooling, natural fresh air, and natural lighting. So natural heating is orientation and mass. Natural cooling uses all of these tools. Natural fresh air is prevailing breeze orientation and window placement. Natural lighting, again, is orientation and shading. So this is just something we just have to start thinking about. And to show you how this whole concept works, I'll borrow some wonderful charts from good friend Vivian Lofness at Carnegie Mellon. She calls natural comfort environmental surfing, all the same thing. You start at a basic energy load for energy use without high efficiency, which in this case for heating is high in the winter, January, and drops to May, starts increasing September, back up to January. So that's how your loads will flow. And when you go with high efficiency, you reduce those loads significantly, and then natural heating takes it down to the next level. So you get about 25 to 75% savings of the remaining heating load after you're efficient. So it's just a free resource to take right there just by leveraging the sun. When it comes to cooling, the load profile is the inverse. So it starts out very low in winter and it gets high in the summer. Now, a lot of these charts you derive for commercial buildings, so you still have some, you'll see some cooling load that you wouldn't have in residential. But the key is the concept that you have your big use in the summer months without high efficiency. With high efficiency, you drop it quite a bit. And then when you go with natural cooling, you virtually just get it down to a small fraction of what it was, 25 to 40% of residual load left once you have high efficient buildings. And then lighting's kind of the same thing. With inefficient systems, you have lighting, you can drop it down with much more efficient LED advanced systems. And then when you have natural lighting and smart controls, you absolutely minimize the requirements, all for free. So that's one side of the equation is the cost savings, but the other side is just the superior user experience. With natural comfort, you actually get what you pay for from the window, the view. And without natural comfort, what you find, people have to pull the blinds down, and the inconvenience of going up and down with the blinds often results in them being closed all the time. You pay for this big expanse of windows for a beautiful view, and just because you didn't leverage natural comfort, it's like wasted effort. And the same thing with just coziness or comfort. You know, mean radiant temperatures have 40% greater impact on perceived comfort than just the ambient air. And when the sun can virtually charge all the mass in a space, you know, the masonry fireplaces, the masonry floors or tile floors, stone counters, there's so many places where mass exists. Even the drywall in our homes has a meaningful amount of thermal storage. And when the thermal mass can absorb the heat during the day, it might even the winter overheat. Now you buffer that and release it at night like a thermal battery. So 40% greater comfort with managing mean radiant temperatures and using the sun to kind of charge your home for the best performance. And the natural light itself is just amazing for health. You know, it boosts vitamin D, wards off seasonal depression, you sleep better, you're more productive. You know, all the science and studies will just consistently just point to these huge benefits. But it's something we all know. You know, we all want natural light and crave it, and it's for good reason. You know, our bodies are telling us it feels healthier. And so no, subconsciously, this is what we should do anyway. And in absence, again, of good natural comfort solutions, we're stuck with the same problem. With the annoying glare, the blinds are drawn, we get no or minimal daylight compared to when we actually manage the solar resource, and we get an abundance of daylight. And you can just see the difference in spaces with windows closed and open. 98% of home builders, designers, architects scored natural light top home feature in 2022. I'm dubious of surveys, but it's way up there. Natural light is always a well sought after feature. And then natural fresh air spaces just live better when it's not overly humid, and we have all those swing season periods when we can just bring in fresh air. It eliminates stale air, makes the whole house feel different. You know, we remove dust, better concentration, better health. So having the ability when we can leverage fresh air to just use the natural wind resource at its best potential is just a huge advantage. So here we have all these superior user experiences: free energy, glare-free views, superior comfort with mean radiant temperature, optimized natural light, natural fresh air, and all the resilience, because these spaces can float so much better, even if there's a power failure. So at zero cost, we get tens of thousands of dollars of added value, and tens of thousands of dollars of utility savings over 30 years of a traditional mortgage. That's a lot of value and savings to throw away for zero cost. We have to be better with zero homes. Then we get down to design with right sizing. And you know, in our workshops on the design side, we cover a whole litany of how we can leverage space and enhance space, all these best practices. And the key you need to know is that you can easily reduce the footprint of your homes, the floor plan, 20 to 40% by leveraging these best practices. And when you do that, like in this example, this is a design I did over 40 years ago, 1,400 square feet that I will submit lives like 1,900 square feet, a luxurious master suite and closets and storage, a 2-compartment bathroom, full living space, a very substantial kitchen with like 15 feet of counter, a work at home space, front porches. You get all this in 1,400 square feet. And again, submit that if it lives like 1,900 square feet, that's 500 square feet of savings at $150 a square foot of hard costs, which are low today. That's $75,000. I've just reduced my cost to build the home and the value I've added to the home because of how much it delivers a optimized user experience, storage, daylight, health, fresh air, indoor outdoor linkages, all the things we talk about in design are all embedded in this to just optimize experience in a home that's right size. And we can't afford to throw away $75,000, $100,000 we can get by right sizing. And complexity just costs money. Simple is your friend. Floor plan, exterior, interior. Again, our design workshops cover these best practices. We go through more detail, but just some examples. If we do a recess into a rectangular footprint, now we lose, let's say in this case, 200 square feet to have a recessed porch. And we've added 12 feet of wall on either side of the recess that are additional wall and foundation. And when you do the math and calculate it, it's costing us almost $3,000 for 200 less square feet in a more complicated footprint than a simple footprint. We have to realize that simple is our friend. We have to build homes that people can afford. These are just best practices we need to do more of. So I just show you that simple design I just showed you earlier, side by side by a very traditional footprint that has the same specifications, 3 bedrooms, 2 baths, and so forth. But in the complicated design, you'll see 15 versus 6 corners. And 9 more corners at $1,500 a corner is over $13,000. And these are older costs. If it's $2,000 a corner, a more updated cost number, now we're starting to push $20,000 just to add complexity with no benefit in terms of how the home lives. So we have to keep asking whether we can afford complexity and be diligent about minimizing it. The roof on the left versus the roof on the right. I think the one on the right's incredibly more beautiful. And we don't even have to talk about all the costs of replacing the complex versus a simple roof. A lot of the discoloration will happen as debris is caught in all these valleys and complicated details. You can see often the water shedding feature of the complicated roof will be much worse. You have substantial amount of water going down to single points, and there are all sorts of issues in terms of the basic function of a roof, which is to shed weather. And the one on the right is like a 10x better solution for shedding weather than the one on the left. So it's cheaper, it's better. We just have to get smarter, especially in zero energy homes. And finally, on design, I want to talk about integrated systems. Now, first, when you have nice, simple roofs, then recognize 2-foot dimensions are your friend. All the sheathing products come there, and it'll be no difference to the truss manufacturer if that's what you're doing to build a truss that's 4.87 slope versus 5 and 12 slope, and you'll save a tremendous amount of cutting and waste and time. It could be $1,000, thousands of dollars of savings. And I'm going to just show you one example where integrated systems, just taken to its most diligent and really focused level, had huge impacts. This was Walsh Construction, did a project in Portland, Oregon, where they already built the first building. It was time for the second building. They started looking at, can we just optimize this and get some really substantial savings? So the old footprints on the left for the individual apartments, for the 1-bedroom apartments, and then you see what they did on the right, and they got it on 2-foot dimensions. They went to a single bath wet wall, much less wasted circulation space, open layout, and they increased the storage substantially. You can see the walk-in versus a small closet in the bedroom, and then when you come in, you have the space on the left for a wardrobe, closet, or a desk, depending what home renters or buyers would want in this apartment. But the key thing is once you do that, then you can put everything on the 2-foot dimensions. So your drywall, your exterior walls, everything's on 2-foot dimensions, and which means less waste, less cutting, less time. And then you can see how simple the floor framing layout is, no waste. Everything is just perfectly serving its purpose. Also, I'll call attention to why that floor framing is going across the unit, not from the hallway to the outboard exterior wall, but across the unit from one unit to the next unit. And then you see the sheathing layout, no waste, very simple. It just, everything's so efficient. And then when you have the articulation for architectural interests, it's also done on 2-foot dimensions, either 2 or 4 feet. Everything's on 2 foot everywhere you go. And I mentioned that they use the floor framing going from one unit to the next rather than from the hallway to the exterior. That eliminated all the headers on the outside because no longer is it a structural wall that needs headers. So that saves framing. And you also notice that across the hallways, which are 5 to 6 feet wide, they just went with a thicker subfloor. And now they get rid of the framing in the hallway and have a plenum for mechanicals. Everything is done to optimize the structure for the home. And you wind up with 42% reduction in framing material from the framing on the bottom, which was done for the first building, compared to the framing above, which is for the new building that was optimized. And you had 16% increase in the whole wall R value because you went from the wall below for the first building to the wall above for the second with all the optimized spacing and insulation. And then a 25% reduction in sheathing. Again, you see the walls with all the cut sheathing in different pieces that are more wasteful than the sheathing plan above for the new design. So the net was that for 124th and Ash in Portland, Oregon, Walsh Construction saved 24% of the cost of the building just by integrating structure into the system design. And the little tweaking on the floor plan also meant for a much better living experience in each unit. So these are big cost numbers. These are the kind of, you can't ignore this if you're doing zero. You have to be focused. And then you have to start integrating structure and realizing you have choices that will impact your objective for providing conditioned space. So this is Oak Ridge National Lab assessment comparing SIPs on the left, a 4-inch SIP, to 2x4 and 2x6 framing options. And I highlight the 2x6 options on the right. The quality installation 2x6 will have a net 13.7 R value. The typical 2x6 will be R11 compared to R14 for the 4-inch SIP. So the SIP is 2 inches thinner. It has more insulation. And if I'm going to try to do the quality installation, I have all the extra work for grade 1 and extra inspections and extra quality control it takes to get a quality installation. So when you look at maybe the higher cost point for the SIP wall, you have to counterbalance it with all the cost savings. I don't have to do grade 1 insulation, inspections, and quality control installation. That may save me $1,000 to $1,500 for the home. All the air sealing and air barriers are inherently built into the SIPs. I have to do all those with the framing. The rework is less, the waste is less, the time could be 5, 6, 7 days less. And then I wind up with thinner walls that create 30 square feet more living space. That's worth maybe $250 a square foot retail. So that's another $10,000 or $15,000. I have more resilience because the SIP walls are much more impact resistant. They're much more resistant to fire. They have less air leakage and less embers can get in, and much greater quality, dimensional accuracy. Everything about them is higher quality. So all that becomes pretty significant when you start to think about what do I do structurally for this design. And also affects you how you select a bigger design of your home. Do I have vented attics or unvented attics? A vented attic has missing the top side air barrier, which to me is a huge hit on the thermal performance of that attic insulation. And then often in Western markets, we'll stick the heating and cooling systems up there for a further hit on terms of reduced efficiency and comfort. So if I go to a unvented attic in my design, now I have all that extra volume and I have basically faster construction, I have more conditioned space, more efficient, more comfort, more strength, more resilient. Again, with the unvented attics, embers can't get into the attic in a wildfire and ignite the framing. In heavy wind, hurricane, and tornado events, the wind can't get into the attic, pressurize it, and just completely destroy the framing. And so you're just more resilient, and you have all the cost savings. You know, all the vents, ridge, soffit, gable you don't need, all the air barriers and air sealing you don't need, and again, all the cycle time savings that happen. So we just have to start thinking about this. How do we get to zero for lower costs? Which solutions do we make integrating systems in our design? And you can see basically a vented attic on the left versus just having a completely six-sided assembly, optimize quality installation for insulation and air tightness. We just have to make our choices and make sure we're considering all the costs and benefit. Again, then we have all this volume. And a good example how that volume can be deployed in the design part of the process and integrating systems, I can make a choice in the design process. You know what? I'm going to trade off the lower level, least valuable condition space, my basement, for volume above grade in the attic. So I'm going to get rid of the basement, go with a shallow frost protected footing, and then leverage that volume. And it may change my roof configuration a little, but again, I now have an upper level that might be worth $100 or more a square foot. And I got much more simple construction. I don't have to build a basement and all the challenges with basements. So I may save up to $6,000 in the basement. I have the gable ends of the wall for free, so I don't have to build those. They're there anyway with the attic, so that's $1,000 to $2,000 savings. I have to do egress windows, all the air sealing and barriers we mentioned at the attic ceiling interface, all the attic venting, the waste savings, the time savings. And then if I'm adding 800 square feet, that's worth another $100 a square foot or $150 a square foot. Very quickly, I'm adding $40,000 to $60,000 of value. These start to become real significant numbers. If we're going to get to zero at lower cost, we have to optimize all our decisions, particularly in the front end when we do design. What will be the best strategy for the lowest cost getting to zero? And the other system that needs to be integrated is plumbing. My good friend Gary Klein is kind of a real innovator with this concept of compact plumbing. What he does is he creates a concept called the hot water system rectangle. You take every fixture that gets hot water, and wherever it is, you draw a box around it. So you can see over here on the left, this is this was a Habitat for Humanity home with a water heater in the garage in the corner. Then you go around to, because you have to get to this sink over here, and you keep going around because you have to get to the bathroom fixtures here, and that creates a rectangle, which accounts for 80% roughly of the 1,600 square foot home. And it's a big rectangle. And what they did was they said, can we optimize this home for plumbing? And they got all the plumbing in 2.5% instead of 80%, 30 square feet instead of 1,280 square feet. So that was a huge reduction. The only trouble was they destroyed the design. This kitchen is horribly claustrophobic. It's a galley kitchen. It uses way too much valuable real estate that's needed for the backyard view. Not to mention they had a closet blocking the backyard view. You wind up with these really awkward spaces for the living room. And look at all the flow that's now in this design. It's just a horrible design. You cannot do that. And where I will differ with my good friend Gary Klein is I don't care about the kitchen sink. I'm not going to be waiting for hot water. As soon as I turn on the kitchen sink, I'm rinsing dishes, I'm using the water effectively. When it gets hot, I can do the more serious cleaning that warrants hot water. I don't care about the sink. So what I would do in this design, you see this domestic hot water heater over here, that's your offender. You want to get rid of that location. And this closet over here is right where I'd switch it, right there. And now this becomes my square and it's 13%. I can live with 13%. All these fixtures will get hot water within seconds. 20 seconds, 15 seconds of hot water. And even the kitchen sink's pretty close to this will get hot water within 20 seconds, 15 seconds. This should have been the solution. And so another message here is you can't get so myopic and just so tunnel visioned on one concept of trying to optimize plumbing. The solution was as simple as relocating the water heater. And I can make up that pantry and other storage so easily with just some more tweaking this design. And if we do all this, by the way, we can get $1,000, $2,000 savings with compact plumbing. So just again, one more integration. And then the last concept, our next concept I want to talk about is mass customization. Again, we talk about this in the module about the future of housing, how we can't afford to build what we're building today. We're building the equivalent of custom tailored clothes that 98% of the, or 99% of the clothes buying public don't want to pay the extra cost for. So we buy clothes instead that's mass customized in factories. It's mass customized to styles, to sizes, and we get what we want so close to what we would get with custom tailored. We're all absolutely happy. I'm going to submit we can actually get as good or better if we mass customize homes with the same concept. We come up with, again, instead of styles and sizes, we have building blocks that we can use over and over again. And because we use them over and over again, we can infuse them with world-class expert solutions, because the cost of those solutions, the health expert, the building science, the materials expert, the color expert, the lighting expert, all the features that could be optimized for each and every building block are then amortized over so many uses that the actual cost per home becomes so small. And then with mixing and matching, we get to strategic design options. So we wind up with what we want: plenty of choice, plenty of diverse streetscape aesthetics, diverse interiors, and huge savings. So example of a good friend of mine who's applied this kind of concept on a small, like 30, 40 home subdivision north of Chicago, was he had A, B, C, D, E, F building blocks he used over and over for every single house. So A, B, C, D, F would be the first floor and the second floor, and those modules will optimize for furniture. They optimize again for lighting, for finishes, for color, for for energy and building science. All this stuff was baked in, and so there you go. And then you wound up with this same concept. You only had always used the same kitchens and bathrooms over and over again. So you had the exterior building blocks and the interior building blocks. And your choices look like this. You can do 2 or 3 stories. You had 2 or 3 truss configurations to create different looks. You had 2 different types of pop-out windows. You had 2 or 3 different front porches, a few siding trim combinations, and a few color packages. And the neighborhood looks like this, completed. And this is anything but a production housing type of aesthetic on the street. It looks like a beautiful, almost historic street. It's such a beautiful job, and it comes down to the details. And all he's doing, he's appending just as like the wrap around the building blocks, different looks to create the interest. And of course, landscaping is something we teach in the design courses. Critical landscape architecture. Once it matures, it trumps the building architecture. So let's move on to now the enclosure imperatives. We have to optimize enclosure, and everyone who's probably at this kind of webinar knows the basics. You've got to optimize moisture flow, airflow, and thermal flow. You've got to control these at a high, almost militant level in these higher risk buildings. And I will submit you can no longer ignore disaster resistance. So airflow and moisture flow, if it's going to come down to managing moisture risk, the most important thing to recognize is that air leakage way trumps diffusion through the sheathing materials, drywall, OSB, whatever it may be. If you look at a hot, humid climate, you take a 4x8 piece of drywall, and on top, you just have that drywall by itself, and on the bottom, you add a 1-inch hole. All of a sudden, over an entire summer air conditioning season, spring, summer, and fall, the vapor flow from the exterior to the interior goes from 3 quarts to 7 quarts of water, or 10 times greater, just with a 1-inch hole. In the cold climate, it's the reverse. The moisture flow going over the winter from the interior to the exterior goes up from 1/3 quart to 30 quarts of water, 100 times greater vapor flow. So this is really simple. Air leakage is way, way more important than just managing thermal flow, no energy losses through leakages. It's got to also, it's imperative for moisture control. And all the air leakage numbers we'll talk about are derived mostly from the energy loss considerations. So there they are for everything from Zero Ready to version 3 of Energy Star to the IECC codes 2012 to 2018 and Passive House. And you have this crazy litany of targets when I'm going to suggest everyone should be at the lowest point for the basic program, 0, Ready, Energy Star, and the IECC codes. Passive House, I think, is pushing too far for the mainstream builders. I think it's a great to have that as a penultimate target, but everyone should be at 1.5. And forget what you can do more leaky construction due to the energy losses. I care about moisture control. I care about indoor air quality. So think about all the dust, pollen, and moisture that comes through. The more leaky the construction, I want it tighter, if nothing else, just for health reasons, and then greater disaster resistance. The more air can get in, the more risk you have to fire, to smoke intrusion, again, for health reasons. The more impact you have from wind and tornadoes and hurricanes that can pressurize the home. Just let's keep our homes at 1.5 ACH50 because it's so readily achievable. I know it sounds like a kind of a big leap for a lot of builders today are struggling to get to 3 or 4, but once the the best practices and tried and true methods are embedded in the workforce that you choose, it's not a hard target. So this should be how we get to 0 cost effectively because it will minimize other dehumidification requirements, will minimize heating cooling requirements. So next part becomes a thermal flow with the enclosure. And this is the array of choices you normally see, from conventional framing to advanced framing to staggered studs, double wall, and structural insulated panels and continuous insulation on the right as the last option. And the thing at the bottom that I included were the framing factors. My buddy construction instruction helped me calculate just the net effective framing factor for each of these choices. And you go from 25 to 30% framing factor all the way down to 2%. I'm going to suggest this block of choices have excessive thermal bridging. I think even 10% is too high a framing factor. So I think anything in this block has excessive thermal bridging. And also, every one of these options has the highest amount of moisture control risk because you're creating more insulation and a colder surface, and you're relying on the field practices to ensure that you have no vapor flow that's not wanted, and that the insulation is installed at grade 1, and it's just so much more cost, time, and effort. Everyone should be moving to one of these 2 options, which is some sort of panel with a structural insulated panel or other factory-made panel system that's high performance and low thermal bridging, or continuous insulation. In the case of SIPs, you get the ensured quality installed insulation. You also get it for the outboard sheathing, more or less. The inboard insulation in the cavity still is reliant on the field practices of the insulation crews. But also this minimizes your moisture risk by, in the case of SIPs, having no moisture flow at all in a sandwich assembly in the continuous insulation. If you pick the right thickness, then you've reduced the temperature enough to negate the moisture risk. If you pick the right thickness, and that's another question. So these are the 2 options where you should be. For me, again, what I like to call attention to is just how many moving parts you're going to manage with continuous insulation. One is you have all the different layers that you have to install in the field, and we know we're losing trades, and we know that managing quality is harder. And then when we get the right thicknesses in most climate zones 4 or 5 and higher, now you're going to need 1.5 inches of insulation, or at least, and then you start to need screws, as you see here. You can't just nail the air gap furring right through, or you have to manage the extra thickness. And all those complications go away with the panels. It's inherently high value. You have 0 moisture risk or moisture vapor flow going through the assembly, better dimensional accuracy, better strength. It has inherent quality in the assembly versus construction. You have added volume, we talked about before, in the walls and the attic, and less carbon, less, about half the wood you would have in a framed assembly. On the savings side, cycle time, inspections, waste, rework, and trades. So just, you need to add all these pieces together and then see how the costs work out. But I'm pretty confident more and more we're going to be moving to some factory-made panel choices. This system of cobbling together all these moving parts in the field we can't afford from my lens. And then finally, disaster risks are so insanely high. The frequency and magnitude of storms is just going up exponentially. I can do a whole session on just where we are at with disaster risk. Enough to say the NOAA maps will tell you there's nowhere to hide. Virtually all the US is exposed to these growing disaster risks. These are billion-dollar climate disasters mapped for droughts, winter storms, cyclones and tornadoes, flooding, wildfires, severe storms, rainstorms. You know, wherever you go, you're confronting risk. So you have to make choices when you pick the enclosure that are good risk management choices. And so when I look at all this, again, I'm going just again to start saying at some point we have to break away from 150-year-old technology and use advanced wall systems. Show SIPs here, there are other choices you can make. But once you do that, when you optimize performance, there's no pathway for vapor flow through a sandwich assembly like a SIP. They're inherently at 1.5 ACH50 max. You have to work hard to go above 1, really hard to get above 1.5 ACH50. The thermal flow, again, you're at 5% thermal bridging, which is, I think, where you want to be or less. And the quality, you don't want to rely on quality field crews with the massive stress on them. We'll talk more about in a moment. So you want assembly versus construction. And then when you have such a inherent high quality assembly that's dimensionally accurate, all your finishes, fit and trim, your drywall, everything goes on faster, better, cheaper. And on the value side, you have more conditioned space, more disaster resistance, again, for fires, for wind, impact. You know, it's just the resistance where you need to be. And on the productivity side, you have cycle time reduction and waste reduction. So you know, at some point, we have to factor all these cost factors and value factors into our analytics to make the lowest true cost choice. And we need enclosures that are ready to deliver zero, that are at lowest true cost. Okay, and also I'll speak to my friend, the Precast Concrete Foundation. This is insane. It uses 70% less concrete, and it's faster, better, and it has so many impressive cost savings. Cycle time, it goes in 5, 6, 7 days faster. It's stronger. It's 5,000 PSI concrete versus 3,000 installed in almost like a bond beam configuration that has greater strength. It's better moisture protection because it is 5,000 PSI concrete versus 3,000 PSI poured in place in the field. You have a clear path to the drain tile for better drainage of the sub-slab moisture. It's much more dimensionally accurate. You have more usable space in the finish basement because of the ribs have the steel caps, you know, the stud caps that you can nail the drywall right to them. You don't have to build a whole separate wall. You can construct it in winter. And again, the savings from cycle time and all the integrated insulation and furring. So again, these systems, I think, really need to be looked at carefully if you want to get to zero lower cost. And lastly, the window. Window is so critical. It is this funnel effect. After you do a great opaque wall assembly, the window is this obvious funnel that you have to manage thermal flow and maintain comfort. And I'll call your attention to some analysis I pulled together from a web tool where you can look at what is the net effective whole wall R value for different wall assemblies, R18, R39, R60 in this case, and a window that is a double pane window 0.30 U value and a triple pane 0.15 U value window. So the Energy Star window on top, a triple pane window below, and I had 15% window to wall area. The numbers would be even stronger for the moving to a more high performance window as I add more window to wall area as our builders are prone to do today. So what happens with a 6-inch R18 wall, when I account for an Energy Star window, the effective R value drops to R11 or at 40% reduction in the whole wall from what is rated for the wall assembly. And if I go to R7, I'm 20%. I lose half basically of the reduction by going to the triple pane. And what's really substantial is the net R14.5 or 15 is just as good as an R39-inch, 13-inch wall with an Energy Star window. I get almost the identical performance. And look at an R60 wall, like a 20-inch thick insulated wall. If I put a triple pane window, I'm within 2.5 R value of that wall assembly that only has an Energy Star window. In cold climates, we just have to be thinking about moving to better windows, and that will save money on the back end on right size heating and cooling systems, and it will just lead to tremendous advantages in performance. So we have two manufacturers that are making really builder grade, cost-effective triple pane windows. Gelwind and Provia, from my sources out there, are telling me that they have a triple pane window that's a really very affordable cost premium above the normal double pane window. So start in cold climates, not just automatically go into the dual pane window, but some manufacturers are really working hard to come up with really cost-effective triple pane options. And then there's also the thin triple, which looks like it's going to hopefully get to market in the near future. But basically, they replaced the normal middle glass layer from traditional glass to the thin glass like you would use for an LED TV. That means the extrusion is no thicker than for a dual pane glass, which saves the manufacturer's cost to retool the plant. And there's also some cost drops in krypton gas that allows for some cost savings. So these windows expect to come in at much lower cost, R5 to R10. And so maybe we'll have even more options for how to get to triple glazing in climate zones 5 and higher, possibly climate zone 4. Moving on to HVAC is the next thing you have to optimize. I'm not going to go through all these numbers, but to say that 70 to 100% of field measured HVAC systems evidenced at least one performance compromising fault. And duct leakage was 2/3 to 100% testing high in a very substantial sample. This is a study done by National Renewable Energy Laboratory. And sizing was a big issue. For 30 to 90+% of homes were testing way too high. So let's talk about the costs of that. You know, when you look at how you design systems, you have location, conditioned floor area, orientation, mechanical system location, and then the thermal assemblies. So we already talked about how right sizing a home is a huge cost saver in terms of per square foot cost, but then it also saves you money on condition area that needs to be heated and cooled for a right size HVAC system. And same thing, we talked about optimizing the enclosure, the walls, the roofs, and the glass. That will also substantially reduce your heating and cooling system. But let's talk about also orientation and where we locate the heating and cooling system. So this is just some engineering calculations, just looking at the same house, one with a south orientation on top and a west orientation on bottom. So you go from 84,000 kBTUs per hour to 60,000 kBTUs per hour, and pretty quickly you have a 2-ton savings on the system. So that could be substantial cost savings, both on the equipment and the ducts, just by getting proper orientation that we talked about earlier. And then we talked about when we go to unvented attics, now all of our heating and cooling is inside the conditioned space. So here's another calculation for the same home with a system inside the conditioned space on top, and in the unconditioned space on top, and in the conditioned space below. So you reduce the load from 74,000 to 60,000. So you save over a ton on the heating and cooling system size. So these are big cost savings that derive from doing all the other things we mentioned about good design, getting the system in conditioned space, orientation, plus using the better enclosure, plus right sizing the home. All those things have a big difference. And once we have a great enclosure, we don't have to worry about bringing the ducts to the extremities. That's just a waste of money. And once, so we can use much smaller ducts because we have a much smaller BTU load in each room, and we don't need to bring them to the extremities. So we can maybe save a few thousand on the duct system. And then there's new kinds of technology like plug and play ducts. This is one system that basically where you, at the plenum, you just basically These holes are punched into the box, and there's these special plugs that create airtight seals, and then the ducts snap into them airtight automatically, and then you do home runs to each room. Each duct does about 20, 25, 30 CFM of airflow. So if a room needs 60 CFM, you run 2. If it needs 90, you run 3. And you basically have great mixing. You have airtight construction without having to factor in the quality of the workforce. It goes in airtight just naturally. And it's just much more simple to lay out. It's so small, ducts can easily go in the conditioned space within any kind of normal truss joist or eye joist where you pop out the hole for the ducts. So this is just something you need to think about as another way to, again, to leverage lower costs for zero. And moving on to productivity, the trade crisis is not going to go away. The Home Builder Institute's latest calculations, over 700,000 new workers needed each year to meet the demand and combat the shortage of 1.5 million homes. So that's pretty stunning when you also look at this statistic that for every 5 aging workers retiring out of the workforce, construction workforce, only 2 in the pipeline coming in behind them. So this is a huge cliff that we're coming to, and the average work age is getting older and older, now almost 43. And this is how we build. We can't afford to do this. We used to build this 150 years ago, and we can't build with the same lack of productivity that we had over over 150 years not to improve productivity. You've seen the same working conditions, pretty unsafe for the worker, all the waste products strewn around the job site, and the supply just sitting there on the ground, probably getting wet. We can do better. This is the only industry to have a negative productivity over the last 3-4 decades. This was a study done by McKinsey and Company. If you look at manufacturing, it's almost double the productivity gains. More importantly, McKinsey and Company quantifies the productivity gap as $200 billion that could be closed by applying advanced manufacturing methods. And also, it's the least digitized industry. Another study by McKinsey found construction absolutely the lowest industry except for agriculture and hunting. And we look at it, to what extent it's using digitization, it's almost all red. It's hardly deploying any amount of really effective use of digitization, which can do so many things. If I build a house virtually on my computer before constructing it, just like every other product is done, you reduce cycle time, you have precise bill of materials that you need, you can schedule better, you have much better quality accuracy installing in the field when everything's completely worked out on the computer first. You know, all the wiring, all the ductwork, all the plumbing, the framing, the connections, when it's all configured on a computer precisely, it goes much better in the field. The integration of all the systems, the machine learning, then you save on the back end with productivity, less waste, less rework. So again, in the cost crisis, these kinds of benefits cannot be not leveraged. And all these productivity factors can be addressed with systems built. You know, the shrinking labor force, the lack of productivity, the lack of digitization. Going to systems built is a huge way to just finally address those devastating shortfalls in the industry. There are a lot of options from framing kits to panels. We mentioned SIPs. There are also insulated concrete panels, conventional frame panels, precast concrete. Modular is volumetric building, or you can mix modular and panels, like modular for the high trade concentrated spaces like kitchens and bathrooms, and panels for the rest of the rooms. And then there's 3D printing popping up in more and more places, making a mark. Some top 15 builders in the country, Centex Communities is 3D printing in Phoenix. I think it's, I forget who's the other builder in Texas using 3D printing. It's faster to do systems built. Huge cycle time savings, 30, 40, 50 days, and eliminates so many trades. It's better quality, better accuracy, often stronger construction. You do use actually more material for framing it. And it does have cost savings for time, rework, waste, and production at scale. So the big savings I want to talk about is time. You know, you still have the engineering and permits and approvals you have to do whether it's systems built or site built. But the big savings is when you go into actually putting the site, the lot development, and the foundations. The difference with systems built at the same time in the plant, you're building the home. You're not waiting for that to happen to start construction. And then when it comes to working in the field to actually get the home on the ground, you're just assembling all the components that are made in the factory versus complete building construction on site built. And then you have all the site restoration process with building normal site built that you don't have with system building. The net benefit's about 30–50% time savings, which is a huge cost benefit. If it's 30 days and we look at Ibicus research on costs of operation for builders per day, $500 to $800, that's just the cycle time savings is $15,000 to $24,000. And this doesn't count the velocity benefits. If I'm taking 30 less days to build, for each additional home I can build in a year, if my margins are 10% on a $400,000 home, that's $40,000 of benefit per additional home I can build. Just every part of being more productive is so substantial. On the cost saving side, it's the carrying costs, it's the increased efficiency of production, and the cost mitigation for so many different aspects of what you have to do to operate your business. Again, your operational costs. On the profitability side, your cash flow is better. You're able to price more competitive because it's less time that you have to carry with uncertainty. You're shortening the bandwidth that for your construction, you can price much more competitive. And the velocity, again, more sales, more closings. For every home you sell because of enhanced velocity, that's a huge impact on your bottom line. And risk, you're building faster, you adapt to the market faster, less risk with inflation and all the uncertainties of the economy. So this is a very substantial impact on business, and it's nowhere included in the bidding process. When I compete a systems built option with a conventional framing option, these substantial cost benefits are completely missing. We got to get to lower costs, and look at how much systems building is used in the US compared to the rest of the major developed countries like UK, Germany, Japan, and Sweden is like the poster child for just how much systems building can be used. The study done in 2019, 85% of new homes were systems built. So let me sum it up and just simply say that if you're going to go to zero for lower cost, the big message today is, most of the presentations I always see around the country and the webinars and everything I observe is so focused just on the energy strategies. But housing is a system, just as much as the house is a system in building science. Housing is a system, and it has to optimize first design. And then product configuration. We can't afford all the customization. We have to configure the product so much more cost effectively than we're doing. And then you have to optimize performance. Your closures, mechanical, electrical, plumbing, health, and all those aspects of performance. And then the construction process. We cannot afford to build with complete lack of any innovation in the enclosure space. We have to use advanced systems built choices, options. We have to integrate all this to get to zero lower cost. You won't get there just by optimizing those factors that I mentioned and showed you in BOP. All this has to be taken into account. Now, in Housing 2.0, I just show you the summary of just tabulations I've done. We're just trying to take these building blocks and really crunch some numbers, and it comes up to about $150,000 to $250,000 of added value for enhancing a home so it can go to zero. We can do this 15 to 20, 25,000 max. So we're talking like 10x benefits that we can't ignore anymore. If we're going to go to zero for lower cost, we have to recognize all these value benefits as well. And we don't in the marketplace, and we don't look at how these homes are sold. So this is just a plug for the next session we're doing, seminar number 5, translating the hidden value of zero, proven behavior change techniques. Once we do all the optimized strategies we talked about today, then we have to communicate the value. If we don't do that, everything falls apart. So we'll talk about 7 tried and true principles for changing behavior that are commonly neglected and how to apply them to ensure customers value high performance homes. When consumers understand value, price becomes so much less important. Famous sales axiom. So thank you very much for attending today. I hope this made some sense. And Mike, I hand it back off to you.
All right, thank you, sir. We're going to go ahead and get to the questions, which we do have a handful of already. And if you do have other questions, please send those in via the chat box. So, first question, Sam, from Zoran. What is the difference, if any, between zero energy and net zero energy homes?
The biggest concepts out there are zero net energy and zero net carbon. And so zero energy and zero net energy are kind of the same thing. That's when your operational energy to run the home is offset by the renewable energy that's either produced on site or from the other options we talked about, microgrids, utility, renewables, offsets. So zero net energy is just when your on-site energy is offset by renewables. Now, the complications we'll get into when you have electric versus homes that are electric and fossil fuel, like let's say gas water heaters and gas space heaters. You know, how do you offset the fossil fuel use for those uses? So it's a little tricky in those spaces, but essentially that's zero net energy. But zero net carbon is when you also consider the embodied carbon, which now, as you get to higher and higher performance homes, is greater than the operational carbon. The carbon that results from the fuels that are used to provide the electricity or on-site fuel use in our home. So what we have to recognize is more and more importantly is that embodied carbon is just this significant increasing force for getting to zero. And so those are the two main concepts, zero net energy or zero net carbon.
Well, and there's a follow-up question that he's got on this. That is, do zero energy, not carbon, but do zero energy homes have to be all electric or get there while still using some amount of gas?
You know, I hate to get into all this granular distinction, but essentially, since utilities only buy back a very small amount above what you consume in renewable power, if you have a zero energy home that uses gas for space heating, let's say water heating and or cooking, the utility will only buy back the amount of electricity that you consume on site. And so it's a zero energy house ostensibly, but you can't put enough solar to offset the fossil fuel use. Now, if you put in an electric car and charge a car, it gets so more and more complicated because is that still a zero energy house or not zero? So basically what I like to advocate is people not complicate things. I believe the more simple we keep it, the more likely we will have to transform the market. So zero energy house is any house that's built so efficient you can offset all or nearly all of the energy with renewable power. And what I'm comfortable with is in the future, if you have fossil fuel, let's say gas water heater or gas heating, you can easily, at very low disruption, change out to an electric heat pump or a heat pump water heater, and eventually the house can get to zero. So, you know, I'll stick with that definition, just to avoid the complexity of that starts to confuse everybody involved.
Well, I'm smiling because some of you may or may not know this, but Sam is actually a guy who went on a tour of seeking answers on vernacular, and that was my first interaction with Sam. I think it was 2014 or something like that. You were basically on a tour of words and trying to define words and get people on the same page with words. And so I'm laughing as we're having this discussion here because I remember those days.
Yeah, let's just all keep it simple. And anything close to new homes that meet any variation of these definitions is a great thing. It's a great thing. And they're easily converted to a full zero in the future because conversion to electric is pretty easy. It's not like I have to change out my walls or I have to change out my, rebuild my whole attic differently. Once you get the enclosure right, the rest can come along for the ride incrementally without a lot of cost and disruption. And that's I think what we should care about. And still call them zero energy houses. Right?
More questions on this topic. So Zoran also wanted to know how soon you expect that all houses, we're talking existing and new, will go all electric.
Never, nor should they. But I expect something like 85% of all houses to be all electric, probably in the 2035, 2040 window, will be about 85%. But there's lots of reasons for why you can still use gas, natural gas heating in certain locations. I'm not militant. I think that's the more I just wrote an article for Green Building Media about why climate's not the greatest existential threat. And I tried to make a case that well-being is, and that we have this horrible reality that we're so polarized because we don't know each other. We don't listen deeply. We don't get seen deeply. We don't hear deeply. And so I know I'm going to offend like half the country if I tell them they can't have gas cooking, or they maybe can't have gas space heating, or I'm going to offend half the country if I tell them they have to use electric vehicles by 2035. I don't need to. The user experience with electric at every step of the way is so much better. Let's just be better communicating the better experiences and providing market-based incentives that promote them to offset all the subsidies that go to fossil fuels. So there's ways we can get there without offending and not being, and also sounding like we're just not listening to how much suffering is going on with those lacking well-being. I know we can get there just by actually listening to people and not trying to take away freedoms and not try to impose all these extra taxes, just ways we can do this.
So here's the follow-up then on, and David wanted to know, can our current infrastructure, we're talking grid and power lines, substations, and even a home's panel, support all electric homes and electric vehicles, or are we going to run into some problems?
Well, if you build the homes with such low loads and you retrofit the existing buildings and houses, and you are smart about how you use electric vehicles, the grid has tremendous different capacity during off-peak than on-peak hours. And we're so flexible how we can charge our cars. We don't need to charge them during peak air conditioning hours or peak even heating hours. We can figure this out how we can do this. And the grid's being augmented with renewable power. So this is not something I'm worried about. It's just about being smarter.
All right. Let's go to the attic real quick here. Deborah wanted to know, what is your opinion of netted cellulose with a vent channel above it?
If it pencils out and it makes sense, fine. But when you do a netted cellulose or fiberglass or any of those options, now I have to have an air barrier below it because I can't allow vapor flow to get through the cold surface on the other side of the insulation. And then on top of the vapor barrier, I need an ignition barrier because it's in the attic and it has to meet the fire code as well. And so all that goes away if I just use that panel assembly, and I have grade 1 insulation and there is no path for vapor flow. It comes down to managing the ridge connection between the panels where they meet. And that's where we ran into issues in the case of SIPs, Juneau, Alaska, and maybe 1 or 2 other places. So, but if it pencils out to do the cellulose with the knitting and then the air barrier and the ignition barrier, then that's the choice you make. I just look at all the numbers and I just want to make sure all the costs are being calculated to get to the lowest way to get to zero. And any way you can get there, but I'm confident that the unvented attic is so superior to a vented attic, and not having a 6-sided assembly and all the volume losses and everything else that we talked about. So just pencil it out. And my intuition is that the panel assemblies are going to be hard to beat.
This one I think is going to be a somewhat easy question. Are ERVs supposed to have dedicated ducts, or are they tied into the HVAC?